All right, good morning, everyone. We're going to get started. So before we jump back into module 4, I hope you all had a chance to watch that video. If not, you should be okay, but try to catch up as soon as you can, okay? And before we even jump right into what's coming up next, I just want to open the floor real quick. If anybody has question, if you watch a video and you have question, please feel free to ask, okay? At any point in this lecture, later on, if you realize that something from the video was not clear, please feel free to interrupt and bring back question from that video as well, okay? Even if we're talking about something different. So you saw the difference in content, probably, right, in module 4. So module 1 to 3, it's about how to program. And we kind of covered a lot of that. Not everything, but a good chunk of it. You guys are already operational on writing code. And now module 4, it's a different type of complexity. So the complexity that people struggle with when they struggle in module 1 to 3 is generally, how do I write code from scratch? That's exactly what we're trying to tackle, right? But now what we're talking about is a more technical complexity. Okay, this is how things work. These are the mechanics of expression evaluation, typecasting, stuff like that. All of those things, we kind of went over them, like going with the flow during module 1 to 3. We didn't stop and think about what was actually happening. Now we're going to do that. That's going to be pretty much the leitmotif until the end of the semester. We are going to revisit things that we already talked about, expression, data type, etc. But this time we are going to drill into more details. Again, it's not a certification course for Java, so we are not going to drill, to the bedrock, okay? But we are going to go significantly deeper. So be careful about that. Be mindful about that, okay? The quizzes that you are going to take right now, the GQ and PQ, are straight from the publisher test bank, okay? I tried to not select the most sadistic question for the GQ. Believe it or not, some questions are going to be a little tough, but I left them in the PQ. So when you are working with a PQ, okay, those questions are going to really drill into your mind, trying to make sure that you understood the smallest little detail about the lecture and the reading assignment. Okay, so expect that. Expect to have like question in the PQ that make you go, I didn't even know, the textbook said anything about that, or I didn't even remember that he said anything about that in the lecture. Go back to the lecture, go back to the textbook, come to office hour, ask us question. You are going to have to be much more active with the PQs, or at least that's my experience for most students, than you might have been until now. Okay, so heads up on how to make the best out of the situation. Now we're going to jump back into the second part of module 4. So it's all about manipulating data. And this time we're going to talk about evaluating expressions, data type casting, and number system. So evaluating expression, yeah, we've used expression already. Data type casting, we haven't used that. Brand new, okay? Actually, we used it, but we used the fact that Java was doing it automatically in the background without even letting us know. So we were kind of going again with the flow. Number system, this is a part that eventually I will remove from the class, but every semester, those of you who took, for example, computer org, or if you took discrete math, etc., you already know what number system are. It's converting numbers from base 10 to base 16, stuff like that. So I'm going to do a quick recap. It's not critical for us, okay? But we just need to have like maybe half a session, a whole session, so that everybody is on the same page, so that you know what hexadecimal is and stuff like that, okay? So we are going to do that as a quick review. If you have never looked at number system, don't hesitate to let me know, okay? Especially if I go too fast through that part, so that I pace myself down and I make sure that you understand, okay? But we're not going to drill deep into that one. Data typecasting, yeah, that one is a lot more relevant for us in this course. All right, so we're going to talk about evaluating expression, but this whole module is mostly about numerical data types, okay? You've noticed that in the video, we talked about like all sort of integer and floating point data types. So as we talk about evaluating expression, we are going to talk mostly about arithmetic expressions And then next module or the one after, I don't remember, we are going to talk about expression that involve, for example, over data type, like strings and stuff like that. So an expression is not just a math expression, but we are going to start with those because you are already all familiar with those kind of expression, right? If you look at the slide here, this kind of stuff should not surprise anybody here. This is like K-12 stuff, right? Basic algebra. So this is a kind of formula that you have been used to manipulate. Well, now that you are programming, there are just a few things to pay attention to, okay? The notation is slightly different. Okay, we don't use just like juxtaposition of a number and a variable to mean multiplication. It's really rare, but once in a while I have a student that does that in a program in this class, okay? So we don't use like the implicit multiplication by just you know what I mean. We don't use a fractional bar like this. So there's just a little bit of syntax, and we already covered that. The star is multiplication, the slash is division. And then there is the fact that we operate in one dimension. So like all those fractions, they make everything really readable. This is a lot less readable than this. I would prefer somebody to send me that than to send me that, but this is what we have to deal with. So sometimes we have to over parenthesize just to make sure that we reflect the structure that is otherwise implicit by a fraction bar or something like that. Okay, so that's our lot. That's what we deal with. And we already covered all of those operators. And the thing that I kept mentioning, and I will keep mentioning it probably for the rest of the semester, is it's not just about the values anymore, or the variable or the values, right? It's about the variable, the values on one side, and on the other side, their data type, okay? So the first time we encountered that was here, slash. What does that mean? Depends. Depends on what? It depends on the data type of the operand. If you are trying to divide things that are floating point numbers, then you're talking about a real division. If you're trying to divide things that are integer, we saw that we're talking about a special type of division, integer division. So those operators here, again, I'm trying to highlight here the difference between basic arithmetics like you know it from math classes and what's happening when you program. There are a few more things that we need to keep an eye on. But most of that, yeah, déjà vu. Those division and remainder operator, there's only one really where we had a lot to say compared to what you had already as a basic understanding, okay? So when do we use integer floating point division? By now, I'm assuming most of you have already built that kind of rule in your head because we have seen examples, but I'm going to make it explicit, okay? This is how Java deals with the problem. I'm looking at the two operands, left and right of the division side. I'm looking at the data type. If one of them is a floating point number, then it's going to be a real division. That's it. So floating point number, now we know that it means double data type or float data type. There are two data types in Java that correspond to floating point number. They differ with their size, how much memory they use, which allows us to store larger, smaller numbers, or in the case of floating point number, numbers with a lot more precision, a lot more significant digit, or a lot less, okay, depending on what you need. So that's it. In doubt, you always go for the larger data type. So if you are trying to divide floating point numbers, you are going to have a result that is a floating point number. That means you do a real division. If you are trying to divide integers, right, you are going to go with the integer data type for the result. You are going to therefore do an integer division and stop before the decimal part. Okay. So we saw a bunch of examples of that, but now that we kind of made the rule explicit, you look at those lines of code and you go through them and you apply the rule, right? Int divided by int gives me an int. One of the two is an int, one of the two is a floating point number. What is the data type of 2.5 here? It's a double, exactly. Remember floating point numbers? The default data type for floating point number is double. Float is kind of like when we want to save memory. Same thing for the integers. The default data type for an integer literal is int. So this is technically int divided by int, right? The result is 2 as an int. Here, this is a floating point literal. So data type double. Double divided by, this is an integer literal, so data type int. Double divided by int, we go with the biggest, double. So the result here not only is 2.5, it's a floating point number, but if I need to know the data type of the 2.5 is double, okay? What if I switch them? Same rule, okay? No problem. So 5 divided by 2.0, same thing. What if both of them are floating point literals or variables of a floating point data type? It's going to be a real division. So, okay. What else? We talked about the modulo. So I'm going to go a little fast about that because we used it a few times, okay? So the only thing that you have to know is that modular arithmetic, it's used in encryption. So if you guys go a little deeper in encryption, you're going to talk a lot about modular arithmetic. But for us, in this class and the next, and probably also the one after that, we use it for this kind of stuff, okay? Little problems where we have like repeating cycles, you know, in a series of values. For example, let's say today is Saturday, so we number the day of the week. Saturday is day number 6, okay? 0 is Sunday. You and your friends are going to meet in 10 days. So you want to say, on a Saturday, I want to add 10 days to that. I'm not talking about the date, right? I'm talking about just the position of the day in the week. So if I go 10 days after Saturday, which day of the week is that going to be? Well, this is the kind of stuff that you use the modulo operator, because the modulo operator does an integer division and then gives you the remainder. So let's take a look at how that works, right? Today is Saturday, that's day number 6 in the week, okay? I add 10 days. I do modulo 7 because there are 7 days in a week. That's going to tell me pretty much what day of the week I'm going to fall on. And in this case, it's a 2, so a 2 is going to be Tuesday, okay? So there are very limited things that we use modulo operator for. That kind of problem, I wanted you to see an example of the kind of problem that we use modulo for, so that when you work through the textbook assignments, right, remember that idea of building block, that idea of pattern matching. If you see any problem like that where you are asking yourself, okay, Saturday is 6, so 1 day plus that is going to be 7, then I go back to 0, then 1, then 2. If you are like counting like that, you need the modulo operator somewhere, okay? And then the second thing that we use the modulo operator for is this number a multiple of that other number? And a special case of that is testing if a number is even or odd. Okay, that just means multiple of 2 or not. Okay, that's it for modulo. So a lot of the stuff that you are figuring out in the reading assignment and that we are covering here, it's not unknown, right? So I'm kind of putting the second layer on top of it, adding some remarks here and there. But if you are still having problem writing code, that means that the time right now, M4, M5, M6, these are going to be the modules during which you can catch up, okay? So as long as you got a good wake-up call at the end of M3, and now you realize, oh my God, I still don't know how to write code, I should be able to write code, that's okay, work with us. We are going to go over this. You will have the time to catch up, okay? Division by 0. What else can I add on the division by 0? Well, we already saw that one, like 5 divided by 0, and when I ran it, it produced an exception. And I didn't say much about exception because really we studied them in COP2513. Okay, we're going to come back on that. It's pretty much when your program says, I give up. I'm going to stop execution right in the middle of everything. There is an unrecoverable error. I cannot do anything about it, okay? So in this case, division by 0 is such an error. But here's the thing that I didn't detail, that I didn't cover yet, okay? What if I do 5.0 divided by 0.0? We were just talking about division, integer division, and real division, right? So this right here is an integer division. This is a real division because of the data type of both operands. Does that change anything? Well, if I ask you to kind of make a leap by common sense, you would say probably, and I would say probably, you don't know, it's still a division by 0. Aha, no. I mean, of course, this is where we're going to start dealing with the little anomalies, the little exception and stuff like that, right? So during the first 3 modules, I try to keep it as clean as possible. Now we're kind of digging into the filth of Java, right? So what we are dealing with here is different type of division. You may expect actually different types of behaviors. There's no guarantee that a division by 0 is going to crash your program when it's a real division. When it's a real division, if we were displaying the result of 5.0 divided by 0.0, it would display on the screen infinity. What is that? that's not a Java keyword. Okay, that's not something that you can type in your code. It's just actually the way for the slash operator to encode the result of this division, okay, as a value. And that value uses an IEEE, I don't remember the number, 754, I think, standard. So there is a very well-defined way to use all those bits to represent positive, negative value, to represent the mantis, the exponent, etc., right? And some configuration of those bits correspond to spatial values. So when println tries to display that floating point number, it reads the bits for the floating point value and it says, this means infinity. So all of this has been established in the standard that we use to encode in memory floating point numbers. What if we have things like this? Well, you put it together. What this slide tells you is that a real division doesn't have an exception, but returns a weird value. And the previous slide tells you when you have a real division, when you have an integer division. So those two examples here are going to also produce this infinity thing. So the reason for which we see infinity is because println interpret the value, okay? So where is that special value coming from? Well, there's a bunch of them. So I'm going to try to give you the lay of the land for that table, okay? Because like when you look at it like that, doesn't probably make a lot of sense. This table is trying to tell you the story of when things go wrong with floating point arithmetics from a computer point of view, okay? So it's going to say, let's say that we have a variable x, we have a variable y. These are floating point variables, okay? So this is the two first columns. And then the table is going to say, well, what happens when x has a finite value? So again, finite is not a keyword, right? That just means it's a value, it's a floating point value that is acceptable, that can be encoded. It's not infinity, it's not anything like that, right? So when x has a valid value, we could call it that, okay? What happens if y is 0.0? And yes, you can have plus 0.0, minus 0.0. Doesn't make any sense from an arithmetic point of view, but you can have it here, okay? So what it's telling you is that if x is a valid number and y is 0.0, then x divided by y is going to give you plus or minus infinity. Again, not a keyword, infinity. That's just a special value. That's just a special series of zeros and one to encode a floating point number that's going to be recognized by every other part of your code as something went wrong. Okay, so if you display it, you get infinity. But if I try to use it in an operation, what if I try to take x divided by y and I try to do something with it in a larger formula? What's going to happen? Well, let's look. We are going to call all of this x. We're going to say if x is infinity, and I try to, for example, divide it by y, which is a valid number, I get infinity. So once you get a division by zero in your formula, it kind of spread to the rest of the formula like wildfire, right? You divide x by zero, you get infinity. You divide this by 3, you still get infinity, right? So this is how you read this table. X and y are going to be put through all sorts of operations, so division, multiplication, modulo, plus addition, subtraction, okay? And you can tell in each of the possible cases what the outcome will be. And sometimes the outcome is okay. For example, if x is valid and y is 0, if I do x minus y, that's a valid floating point number. No problem there, okay? So there are cases in that table that are okay, that tell you, yes, the show goes on, I still continue doing my computation. But what you're going to spot real quick is that when you get one infinity here, it tends to propagate in some of the arithmetic operation. And sometime you are going to get something called NaN. And it's not delicious bread. It's actually an acronym that stands for not a number, okay? So that's happen if x is 0, y is 0. And for example, I try to divide x by y. Not a number means I cannot even represent that, not even with a special code, okay? Sometimes I can tell you that number is infinity or minus infinity. Yeah, we can use that in mathematics in certain contexts. But this is, I cannot compute this. 0 divided by 0, your result is not a floating point number, NaN, okay? So the problem with NaN, again, not a keyword, right? It's just a special value. The problem with NaN is that if you get it in X or Y, right? No matter what operation you are going to try to do with X and Y, it's going to give you not a number. So once a part of your formula results in the NaN special value, like everything you're going to try to do around that value is going to still result in NaN. So it propagates the error pretty much. It says you obtain not a number. I don't care what kind of arithmetic operation you do on that. If you do an arithmetic operation on something that is not a number, you get not a number. Okay? So if I try to display this, it's going to display NaN. If I look into my variable with a debugger, it's going to show me NaN as a special value inside. Generally, things do not go well. When you do stuff like that, there is probably an error in your formula, okay? Or you misunderstood the formula or something like that. So you need to go ahead and not only debug your code, make sure that you implemented the formula that you had to implement correctly, but if you did a good job implementing it, then you need to talk to your client and see, what kind of values should be acceptable for the formula. What is its domain, right? Because obviously you just entered some value in your code that makes the formula explode. Okay. All right. So let's keep talking about floating point numbers. Floating point numbers are actually fun. Fun in the sense that if you can avoid them, avoid them. Okay. It's that kind of fun. Let's take a look here at the system.out.println. System.out.println 1.0 minus 0.1 minus 0.1, 0.1, 0.1, 0.1. Okay. So this is an arithmetic expression that I pass to my system.out.println. The arithmetic expression is using subtractions. It's using floating point number all the way. So I don't even have to worry about, is the result going to be an integer or floating point number? No, it's not going to be floating point number. What is going to be the data type of the result? Double, right? Because this is a literal, a floating point literal, default data type double, 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 put a bunch of double together, do some operation, you get a double result. Okay, what's going to be the resulting value? 0.5, right? Okay, so that's what anybody would say, except if you fail your sanity check, right? What about the second one? Same thing, double operation, that should be 0.1. Well, let's run this. Here's the first one. Yeah, that's cool. So it is kind of 0.5, okay? It's a double floating point value. So it has a lot of significant digits, like 16, I think, if I remember correctly. And at the end, it says it's 0.5, 0.00001, okay? So there is this little one at the end that is insignificant, right? But it's there. So that's going to cause some potential problem. What about this one? That's the representation of my 0.1. It's 0.0999999, and just 8 here because you have to keep the fun going. So yeah, that's the problem with floating point number. They are a little quirky. It's all based on the representation, okay? The way that we represent floating point numbers, we have to represent them in binary with zeros and one. We have to apply a certain encoding, which is IEEE 754, okay? All of this means that these are not the floating point numbers that you guys have been playing with through K-12, college, high school, stuff like that. These are not real floating point number. They are computer approximation of floating point numbers, okay? If I ask you what is in like just regular, everyday life, if I ask you what is a third, 1 divided by 3, 0.33333, and it keeps going, right? There's a repeating period here of 3. All right, so what does that tell me? That tells me that there are some numbers, some floating point numbers, even in real mathematics, right, that we cannot represent absolutely correctly. That's why we use fraction. If I write 1/3 and I use that in my calculation, 100% correct, 100% accurate. If I enter in my calculator, if I enter 1/3 the calculator tells me this is 0.333333, and it stops at 10 digits, this is an approximation. So when I do operation on 1/3, then it's going to keep having an approximation of an approximation of an approximation. I might end up with a result that is not just as neat as if I was pretty much computing algebraically the result. Okay, 1/3 multiplied by 3, that's 1. Well, if you do it with a calculator, it might not be 1. It might be 0.333 times 3, which is going to be 0.999. So this is not a new problem, okay? So we encountered that like in our everyday life using the what we call the decimal system, which is, I have digits that go from 0 to 9, okay? So we use a basic decimal system in everyday life. We use floating point numbers in everyday life. We don't call them that, we call them real number, right? And we have seen those problems of having precision issues. This is just the same kind of stuff going on here, but throwing a little bit of binary coding, throwing a little bit of, I have only this many bits to represent the mantis, this many bits to represent the exponent. So pretty much this is approximation all the way. And there's not much we can do about that, unfortunately. But you have to be aware of it, okay? Otherwise, sooner or later, you're going to bump into some weird bugs. You're going to get weird results in your code. You need to determine whether it's actually a mistake on your part or whether it's just because you have been using floating point numbers and then approximation after approximation. Yes, at the end of the day, your bank accounts are off by, 23 cents. Did I miscompute? No, maybe not. Maybe it's just that. All right. So that's the first thing that we need to be careful of. And I mentioned bank statement because this is the example that everybody uses when we talk about this for the first time to students, like the textbook uses it as well. If you were actually to track some form of monetary value in a program, most likely I would recommend that you use integers. So instead of saying, $1.23, what you want to do is you want to store in your variable 123 cents. It sounds like nothing, but you just went from using floating point numbers to using integers. So as long as you total up all of your currency values in cents as opposed to dollar, you are going to have round number. You are going to have perfectly accurate arithmetic. And then when you need to display the total balance of a bank account to somebody, you just divide by 100. That's it. And you're going to say 123 cents is $1.23. But all the time that you do subtraction, addition, division, multiplication, etc., you do them on integer data type to have full accuracy, okay? Let's keep playing. So there are other implications. There's an implication about, accuracy, rounding up and down errors, that come for free with every use of floating point numbers. And then there are things that relate more directly to the stuff I taught you during module 1 to 3. So I didn't lie to you during module 1 to 3, I promise you, right? But it's just that I try to avoid the edge case, the weird stuff, etc. Now this is time for weird, right? So here's a loop, okay? It looks like a counter control loop. I initialize a counter. I keep watching for a value that is going to tell me when to stop. And then I decrement the counter by a small value here, and then I display n every time. So it's a counter control loop, like we've seen. But there is a reason for which, like during the last 4 weeks, I only made you work with counter control loop that we're using int counters, integer counter, right? Because now I'm switching to a double counter. Should it make a difference? No, and that's the problem. That's why we spend all that time discussing that, so that you remember it, okay? If I look at this, I say I start at 1. 1 is not 0.5. I decrease by 0.1. So now I'm at 0.9. 0.9 is not 0.5. I decrease by 1. I'm at 0.8. 0.8 is not, etc. I decrease by 1, 0.7, 0.6, 0.5. Now this is false. I get out of the loop, right? That's actually the theory. So it's nice. And the problem is that I can look at this code, all day long and tell myself that story. And I'm not completely crazy. I mean, this makes sense, right? But I'm completely forgetting about one little detail. The fact that those imprecisions are going to creep up, right? So the first time I do 1.0 minus 0.1. Okay, there's a finite way to represent 0.9 in binary and using the IEEE 755-54 standard. So yeah, I got 0.9 in n. Then I will subtract again 0.1. Again, 0.8 can be encoded accurately, so I get 0.8. And then I don't get 0.7, I get 0.700000001. And from there, it keeps going down like by one, but I still carry around the string. And then it's starting to get like really funny here. This is 0, by the way. This is like scientific notation, 1.38 exponent minus 16. This is very, very close to 0, but it's not 0. Yeah.
I'm not sure if it's not already, but why does it all of a sudden just throw into one? Like, why is it?
So it's because it's trying to represent a number using a finite number of bits, right, in memory, like 32 or 64 bit, depending on if you use float or double. And it's trying to encode that number in binary, right, 0 and 1. So it's exactly the same situation that we encounter in everyday life. When I tell you, for example, I tell you, for example, can you please compute 1/3 multiplied by 3? And it does it algebraically, right? 1 divided by 3 times 3 cancels, it's 1. So you get full accuracy because you worked with fractions. Now, if I tell you, can you do for me, please, on your calculator here, 1/3 multiplied by 3? If you actually use a calculator, 1/3 is 0.33333333. Oh, I have to stop. I have to stop because in computer science, we use finite number of digits, binary digits, to represent numbers. So I cannot say it's 0.333 with a bar over it. That means infinite repeat, right? No, it's going to be 0.3333, 16 of those threes, and that's what I can do, the best I can do with a double. And now you multiply that by 3. 3 times 0 is 0. 3 times 3, 9. 3 times 3, 9, 9, 9, 9, 9, 9. So now you get 0.99999. The difference between the two, you use fraction, you use an encoding, a decimal encoding of a fractional number. Does that make sense? So here we don't have a choice. Okay, we do have kind of a choice. I'm going to mention it after we're done talking about this. Okay, but if we use a double data type, if we use a float data type, that's it. That's what we have to deal with. Okay, just the same way that if I force you, you tell me, well, I can do 1/3 multiplied by 3. But I tell you, no, I don't believe you, I don't trust you. You have to use this cheap calculator. And use a calculator, you're going to come up with an approximation, right? So we are using sometimes expensive calculators here, but they still have approximation issues. Yeah. No, very good question. No, that's a very good question. Any programming language does that. So let me jump back to what I said I was going to answer afterward. Can we really not avoid that? We kind of can avoid it, okay? Modern language come with specialized library, scientific computation library that are pretty much implementing like very advanced math stuff. And one of the things they implement that is not that advanced is pretty much infinite numbers. Numbers where we have, as many significant numbers as we need or stuff like that. Or we have library that allow us to work with fractions. So when they evaluate 1/3 multiplied by 3, they are not going to try to compute 1/3. They are going to try to evaluate, I should say, instead of solve, to evaluate algebraically the formula. Okay. So yes, there are ways around that. Okay. But for mainstream computing, I'm trying to remember if I ever used the scientific computation library. I don't think so. I need to learn NumPy because everybody's using it right now, but that's about it. Okay. So that's for everyday programmer. This is very much something that you need to keep an eye on. Okay. What else? So yeah, the funny thing about that is that my stopping point was 0.5. So I reached 0.50001. Well, when you compare numbers, you compare for equality or difference, right? 0.5 is different than 0.5000001. So that means now I got myself an infinite loop. Okay. So the reason I use this example is to show you that it can manifest different ways. It can manifest in terms of, oh, my result looks like it's off. by like 23 cents. Or it can manifest itself as, that's weird. I have a loop there, a counter control loop that iterates 5 times, and now it's infinite. Yeah.
Truncate that by, so that you only use so many decimal points, so that it would wait.
You can do that. So that's a good suggestion. We could round up, round down, okay? It's just going to make things a little more, okay, well, it's going to make things a little more complex because as long as you know how you need to round up or down, sorry, and you can be consistent with that all through your program, then you're okay. But if sometimes you need to round up, sometimes you need to round down, you just add another layer of worries pretty much for whoever is implementing this code, right? It's like every time I'm going to do an operation on a floating point number, I have to worry about, okay, what can possibly be the result? How can this result interact with the other part of my code? That's hopeful, right? And then there's a more philosophical argument here that says, if you decide that you want to change, for example, the number of significant digits to something smaller, why don't you go to a float instead of a double, right? That would do that. Well, yeah, but no matter how many digits you have, how many significant digits you have, the flow is intrinsic to the representation of the floating point number. So instead of having 0.700000001, you are going to have 0.7000001. But you're still not in better situation, right? So it's really tricky, and that's why we spend the time to mention it. Not because I expect you to do a lot of stuff about it. I'm not going to try to trick you with that. But if in the odd situation where you have an infinite loop like that, you need to be able to come to the conclusion that this is not me. This is the floating point number. There are things that we can do actually. So instead of actually comparing to a number like this, we can actually try to compare to boundaries. So let me see if I can. I think I'm going backward here. There we go. All right. So this version of the code here is more robust. We encountered something like that already. Remember that infinite loop that skipped over 5? It went 0, 2, 4, 6, and then I was looking, my condition for the while was as long as the counter is not exactly 5. Well, I figured out that if I was skipping 2 by 2, I would skip over the 5 and never detect it, right? It's kind of what's happening here. I didn't skip over the 5. Well, actually, as a matter of fact, I kind of did, but not because of me adding 2 at every iteration, just because of the imprecision of floating point numbers. So if I want to make sure that this kind of loop is foolproof, if you are using a double counter, make sure that you avoid testing for exact equality or exact difference. Okay, these are like traps for floating point numbers. Instead, use a greater than, greater equal, something like that, right? So here, n equal 1, as long as n is greater or equal to 0.5, keep going, or greater strict than 0.5, keep going. Here's what's going to happen. If I don't want that last iteration, I'll have to change things a little bit here, for example, right? But at least it iterates a finite number of times. So it's a lot better, right? But still, I didn't fix the problem of representation. I can't. But I worked around it. All right. Well, that's kind of the same problem, but that's not a loop. Okay, so it's still the same rule. Never trust equality or difference comparison, so equal equal or exclamation equal, when you are dealing with floating point numbers. Here, I'm just saying I'm going to make a computation, and then if my result is 0.5, but that could be anything, right? If my result is 0.27, if my result of the temperature divided by the barometric pressure, etc., is 107.8, and I test equality. And then if at any point of my computation, there was an imprecision that propagated, well, this is not going to work. So we know that this is not giving us, 0.5. So this program doesn't trigger this condition as being true. It doesn't actually trigger the system println. There's nothing on the screen. Okay. So again, weird symptom. My code is not displaying something, but I did the computation by hand on paper, and it's correct. Yeah, you forget about floating point numbers quirkiness. Okay. So what do we do when we want to check if the result of a floating point computation is actually 0.8 or 0.9 or 0. Whatever. What can we do? Well, we can actually test with intervals. So for example, and this is a little funky, but this is because I didn't introduce yet Boolean algebra to you. So Boolean expression where we can say a condition is this is true and this is true. So I wrote it with two if statements. So a little bit wonky, but it's still working. If I have this and I want to check if my result is 0.5, I'm going to have to check first that n is greater or equal to 0.5 minus a very small value, like minus epsilon. Okay, you've seen those formula where we say x is between this value minus epsilon plus epsilon. So we use generally the Greek letter epsilon to represent a very small value. In this case, the small value is 1 exponent. So this is a floating point number in scientific notation, minus 12. So 0.000000001. Okay, tiny little number. So what I'm saying is that if n is greater or equal to 0.5 minus that little epsilon, then I check if n is less or equal to 0.5 plus that little epsilon, I define a range. I defined a range around the value 0.5, a little bit before, a little bit after. If you fall within that range, then I'm going to consider that you are 0.5. And I know it's not 100% accurate, right? But for the sake of detecting if my result approximate 0.5, that's what I need to do. That is how you detect that n is equal to 0.5 with a precision of exponent minus 12. Okay? That's what you have to do. You have to manage those uncertainties. Okay? And that's it for the warning on floating point number. Okay, you are well equipped now to at least distrust fundamentally floating point numbers. If anything, that's actually a good start in your life writing programs. This slide here, very quickly, we saw definitely this one. Okay, I'm showing you real quick some of the most common math method that are available in the JDK. The math.sqrt square root, we have seen that one. I don't think I mentioned that one yet. Math.abs, absolute value. And you can note that the square root and the absolute value, they work on parameters that are double or that are int. Okay, so you can pass an int, you can pass a double. Same thing here, positive, negative, doesn't matter. And then the POW, power, okay, 2 to the power 3, you write it like that, power 2, 3, and you can use, again, integer values or floating point values. Yeah.
So it works with literal values that are both integers and doubles, but if you put in, say, a variable instead of a floating point or those kind of values will also work too?
Yes. Okay. So very good question. So everywhere, I think that you can take this home as a very general rule of thumb. Okay. You may have noticed it already in module 1 to 3, but I'm telling you officially right now, everywhere you see me using literal values, okay, you could replace that literal value by any expression that yields a result of the same data type. So if I tell you one day, hey, I have this nice little method, you can call it, and it takes one parameter, which is, let me show you an example. I can put 5 here. In your head, generalize. I can put 5. I can put any formula that's going to give me an int. I can put any call to a method that's going to return to me an int. So you can chain methods call into one another. We're going to see an example of that in a few slides, to really make a point out of it. Okay, but yeah, that's a good question. Everything that is of data type, like for example here int and int, can be substituted. So your question was more specific. It was, what if it's a float instead of a double? Like you expect a double here is a float. Okay, yeah, because if I get a result here that is a float, remember floats are that big, doubles are that big. So let's say that the method say, I only take doubles. I give a float. The float is small enough that it can fit in a double, no problem. So Java does data type casting for us. That's the next topic, right? But it does it automatically. So we never had to talk about it, even until last week, because if I give you a small floating point number and Java expects somewhere for whatever reason, a double floating point number, it's just going to pad it. It's going to take the 32-bit representation of the float and put it in a bucket that is 64-bit large. You can always do that. The problem is if my method tells me I only want float as parameter, and we try to shove a double when we call it, right? So now there's a problem. This is my bucket. It's a 32-bit float. You call my method expect that 32 bits of float encoding, and you give me 64-bit, you try to shove it into the 32-bit. Not going to work. The compiler will catch that, okay? Same thing with integers. You want an int? If I give you a byte, if I give you a short, they get upgraded. But if I give you a long and you expect an int, now we have problems. I gave you something too big, pretty much. A data type that's too big, okay? So build that intuition about sizes. Data type size, they are not the same size. They cannot accommodate the same range. You've seen that in the video lecture. So you cannot force something, a value that is big, into a smaller data type than the data type of that value. Okay, very good question. Thanks. All right. So we are still dealing with evaluating expressions, but I want to just do like 4 slides, 4 or 5, I don't remember, on the assignment operator. And I kind of told you already a lot of stuff about assignment, including the fact that you can chain assignments. We're going to review it real quick if you don't remember. But I have more to give you here. There's more syntax to allow you to assign values to variables in Java. And it's just that, syntax. Okay, so you know the deal with syntax. You learn it by heart. Okay, I can tell already, based on office hours and stuff like that some of you are experiencing problems in the class, but we can trace that back to the fact that you didn't memorize some things, right? So trust me when I tell you that. When I tell you, your building block, you need to memorize them 100%. Yeah, it's going to be a pain otherwise to go through the rest of that class. So those syntaxes here, that's just what they are, syntaxes. Memorize them, get over it. It's not fun, but get over it. And now you can start using them in your program. So plus equal, minus equal, star equal, slash equal, percent equal, no space in between, right? So these are what we call augmented assignment operator. And they are just a shortcut notation. So instead of writing I equal I plus 8, which I diligently did for 3 modules, but you're not going to see me write this ever again for the rest of the class, right? I did it for the first 3 modules because I didn't want to bombard you with like 3 or 4 different syntax. It's stupid. Let's learn one syntax, let's learn how to use it, right? So every time you want to increment a variable, I told you it's, for example, n equal n plus 5, or n equal n minus 8, or n equal n times 8. Every time you modify a variable and you want to say, I take the current value, I do something with the current value, and that's my new value, you have been following that pattern, okay? Name of the variable equal, and then an expression with the name of the variable in it as well. What I'm telling you right now is that for those simple cases, and we encounter them a lot, okay? I want to increment my variable by 8. I want to decrement my variable by 8. I want to increment my variable by multiplying it by 8. I want to decrement it by dividing by 8. I want to apply the modulo on my variable, okay? For all those cases, you can use the shortcut notation. And that's all the compiler does. You type 1 plus equal 8. The compiler translates first into I equal I plus 8, then pass it through the rest of the compiler. This is your bytecode. This is what gets executed. So it's nothing new. You don't do anything special. You just allow yourself to write things in what is considered a more readable way by experienced programmers, okay? Nobody likes to write I equal I plus 1, etc. It's not a big deal, but that has been like that for like decades now, so you need to be aware of it. So it's just a shortcut notation, no biggie. But you need to memorize it and understand how it works, okay? These ones are more fun. So some of you already took the CGQs, okay? And some of you already scored perfect. So I know that at least some of you have already encountered those assignment operator. There are special assignment operator. We call them pre or post, depending on which one we're talking about, increment or decrement, depending on which one we're talking about, unary operators. Unary operator, let's start by this, by the end. Unary operator means it's an operator that takes one operand, okay? So for example, I can write plus plus followed by the name of a variable, plus plus x, okay? Or I can write x plus plus, or minus minus x, or x minus minus. No spaces, again, in that stuff, okay? So that plus plus and minus minus, these are my two operators. One increments, one decrement. Guess which one, right? Plus plus increments, minus minus decrements by one. So first thing to understand is those operators, they are meant to work with integers. You cannot plus plus a floating point number. You cannot minus minus a floating point number. You can only do that on integer, long, byte, and short, the integer data types, okay? So they are meant to say, I want to increment this variable by one, or I want to decrement this variable by one. So, okay, we talked about unary operator. This is an operator that has only one operand. We talked about increment, decrement. So these are the version that increment, these are the version that decrement by one. And then what is that business with pre and post? Well, pre and post refers to whether you put your operator before the name of the variable, so that's called pre-incrementation, or after the name of the variable. In this case, it's like post-incrementation, right? Pre-decrementation, post-decrementation. What does that mean? That's the thing that you need to understand. That's the thing that's going to cause bugs if you don't, okay? Let's take a look at the pre-increment operation here. The idea is the way that this is going to be evaluated by Java is going to involve two steps. The first step is, because it's pre-incrementation, before to do anything else, the first step is increment that variable. So Java is going to increment the variable by one. So if I add in variable var 23, now I have 24, okay? That's the first step. Makes sense. It's an incrementation operator, you know. Second step, this might appear in a formula. So that means that once you're done evaluating plus plus var, you expect the result of that to be, for example, added to 5 or something like that. So this is where it's important. The second step for this pre-incrementation operator is now we use a new value of the variable var. So the 24 in my example, the one that we just incremented, we use that new value and we substitute this by the new value in the formula where it appears. Okay. So if I say plus plus var plus 5, let's say var is 0 to simplify, plus plus var is 1. Now I'm left with 1 plus 5, 6. Okay? Well, that's not going to be the same every time. So in this case, like with a j and I, if j is 2 to start off with, I is 2. Sorry, not to start off with. Where are my I and j? They should be defined somewhere. There we go. Assume that I equal 1. Okay, so j is not yet assigned. I equal 1. Plus plus I means the result is 2, and the variable I contains 2, right? I assign 2 to j, so both the variables contain 2. Okay, and this is going to be different for each of those 4 cases. Let's take a look at the next one. The next one is post-incrementation. So what does pre and post refer to? It refers to, do you want to use the new value of the variable, or do you want to use the original value of the variable before it was incremented? Okay, and it's not really like, how to say, it's a little confusing to some students every semester, because you would think pre is I use the old value, post I use the new value, but no, it refers to when you apply the incrementation. So pre-incrementation, first you increment the variable, then you use the new value. Post-incrementation, first you increment the variable, but you use the original value. So you can see it like that, or you could switch those lines and say, well, first I use the value and then I increment. Whichever fits better in your brain, you tell yourself like whatever narrative you remember it, okay? But the idea is that if I have, for example, here I equal to 1, okay? Because I wrote I plus plus, and this is in a larger formula, right? I plus plus, I'm not going to increment I right away. To evaluate this expression, I'm going to say, okay, I plus plus is going to be equal to the current value of I, 1. So I'm going to assign 1 to j. And after I use 1 to replace this, I'm going to increment I by 1. Okay, that's what it says here. There are different ways to say it, but it says, yes, you will increment the variable by 1, but you use the original value to substitute this part. That's it. Okay? Those two, if you understand the first two, the other two are just following, pre-decrementation, decrement the variable, and then use the new value. So there we go. Decrement I is 1, so 0. I use 0 to substitute for this. 0 is assigned to j, so both j and I are 0 at the end. And then the last one, post-decrementation. So first, I'm going to decrement I, right? But I substitute this by the current value of I, which is 1. Now I decrement the variable I, it goes to 0, and I assign 1 to j, so j is 1, I is 0. Does that make sense? It will, okay? Just reread it if it's a little fuzzy, reread it a few times, it will make sense. It's a little surprising the first time you encounter it, maybe, but you're going to get the hang of it. And you're going to see a nice example in actually the GCQ as well to reinforce that, okay? So if we wanted to talk about, because these are like just shortcut notation, we could completely write code, be successful programmer without using this notation. So why do I teach them? Well, first, I don't teach them to you for the 3 first modules, because really they're not necessary. And second, I finally teach them to you now in module 4 because everybody else uses them. So I cannot let you get out of the class, without having heard of those. But as far as I'm concerned, when you write code, you use whatever notation you are comfortable with, at least for this class, okay? And next class, then we'll talk about, best practice and stuff like that. But for this class, get your code to work. However, when you take a GQ, when you are given code, if the code uses those notation, you need to be able to read them, okay? So that's like the level of expectation for this class. So let's take a look here at a piece of code that says int I equal 10, then int new num equal 10 times I++. That's translated by the Java compiler to this. So it just says int new num equal 10 times I. So I use the current value of I. And later, I increment I by 1. So maybe, that's clearer to visualize like this for some of you. That's exactly what we just discussed in the previous slide. Just another way to look at it. When it gets spicy is when you are trying to use the plus plus and minus minus on the same variable that appears multiple times in a formula. So again, for the sake of, this is my first time programming, don't use those if you don't feel like it. Write simple code that works, okay? And progressively, make sure you understand how those work. You can read code with those and progressively introduce them into your practice, okay? But like at this point in the class, if you are a first-time programmer, this kind of expression can be really off-putting. So I have this kind of expression in the CGQ, yeah, because you need to be able to read them even now, right? But I wouldn't write this kind of code except if I'm confident that I know exactly what I'm doing. What is the problem with this kind of code? Well, the problem with this kind of code, if I try to trace it, is that line 7 is going to take me a bunch of steps, actually. So let's do a trace table real quick, right? Line 5, k equals 0, all right? Line 6, n equals 42, all right? So far, so good. And then line 7, well, I'm going to use that notes column here, okay? So line 7, before I start execution of line 7, okay, so this is the end of line 7, but before I start execution of line 7, n is 42. I interpret this formula. I'm going to focus first on plus plus n. So plus plus n, it's pre-incrementation. The incrementation comes first. Increment n. Okay, you got it. N is now 43. And then what I'm left with is this is replaced by the value 43. It's pre-incrementation. And I'm left with 43 plus n plus plus. And I'm not done with my evaluation. So my evaluation is going to take me several steps. So now I'm evaluating 43 plus n plus plus. So I focus on n plus plus. Post-incrementation, what is n? N is 43. So n is going to be incremented to 44. But I don't use the new value, 44, right? Because it's post-incrementation. So I'm going to substitute this again by 43. And so the last step, I have 43 plus 43. I evaluate this, no trick this time. That gives me 86. I assign 86 to K. So no matter how you look at it, if you know how this works, use it. Makes for better code, actually. If you are not 100% sure, try to use it during practice. In the middle of an exam, try not to use that, okay? If you're not really sure of your footing, okay? Yeah. Oh, that was your question? Yeah, definitely. So yeah, go progressively with that. You can write perfect code without having to use that trick, but you need to know it exists. To finish off on assignment, expression versus statement. This is just a side remark. That one is kind of anodyne. It's not hurtful, okay? It's not going to cause you problem. But there are things in Java that can be a little weird sometimes, counterintuitive. The fact, that we differentiate between expression and statement. What's the difference between an expression and a statement? A statement does something. An expression is something that you evaluate, like a math expression or arithmetic expression, and you get a result. So everywhere you use an expression, the whole expression is going to be substituted by its result. And then you're expected to do something with that result. Well, it used to be that in Java, you could write, 23 semicolon, and the compiler was happy. That doesn't mean anything. 23 semicolon, that doesn't mean anything. That means here's the number 23. Please don't do anything with it. End of statement. Okay. But if I put 2 plus 5 semicolon, it's an expression also. I evaluate it, 2 plus 5, so I compute the result of 2 plus 5. Now I have 5. What do I do with it? Nothing. Now, if you write x equal 2 plus 5, yeah, it's a statement. You assign a value to x, okay? So Java makes the difference between statement expression, and since Java 2, these are the only type of expression that can be allowed as standalone statement. So you can write plus plus n, semicolon. It's only half stupid. Not stupid because of what we wrote, stupid because of the way Java interprets it. Plus plus n means increment the variable n, so it was 0, now it's 1. And then you get the new value, 1. And what do I do? 1 semicolon. Well, it's sitting there, that's it. I'm not doing anything with the value. So I'm not using the result of the expression, but I'm still allowing you to write this because plus plus n actually has a side effect. It also increments the value of the variable in memory. Variable plus equal expression, variable equal expression, the basic assignment that we talked about, it's also an expression. If I assign 42 to the variable x, remember what I told you? 1, you shove the value 42 in the variable x in memory. 2, the expression for, x equals 42 has itself a value. So I could use it in the middle of a formula. Well, Java allows you to do that because, yeah, the assignment has still a side effect. So here are some of the examples that I already blurted out, okay? So 23 semicolons, the compiler tells you, no, are you out of your mind? What do you want me to do with that? 2 plus 3 semicolon, are you out of your mind? You compute a value and then you don't ask me to store it anywhere or use it in a more complex formula. And then this is getting funny. What if I write math.square root of 36.0? I call the method square root. I give to it the value 36.0. It computes for a few milliseconds, what is the square root of 36.0. It returns the result. And now this is substituted by the result. So 6.0, semicolon, still allowed. Still allowed because Java is not going to discriminate on method call. So building block, 3? It's not going to discriminate on method call because it really doesn't know what the method is going to do. It's going to return a value, but maybe it's going to also store that value in a log file, write something, over the network to send a request to a REST API or something like that. So the rule is, you are wasting my time. You're wasting my time. Even if this was like the same value, right? 5, for example, the Java say, you may be wasting my time, but I cannot tell. So I'm going to allow you to call the method like that. And even if it returns a value and you don't use it, okay, I'm assuming you know what you're doing, right? But that's kind of inconsistent, right? Kind of a little weird. And then those guys already explained, yeah, Java is going to allow you to write statements that are actually made of that thing. And that thing, it does 2 things, right? It increment n and return yields the value of the variable. Well, you are going to still increment n, but you ignore the value that is pretty much computed, right? You don't use it in an expression, you don't assign it to anything or anything like that. Last, and then we'll be done with everything that I can think of and everything that's in the textbook regarding expression. Okay, there might be some over advanced trick, but I cannot think of them right now. So the last thing we need to talk about, it's something that you are already familiar with. It's called, in jargon for computer science, programming, etc., it's called operators precedence and associativity. So these are two properties of each of the operators. But really, it's something that you already know, even before you didn't call it that, okay? When I give you an expression like that, immediately, what do? You target the parentheses, right? You look at the innermost parentheses, and you evaluate that. So 4 plus 3 is 7. You substitute the result. Then you are left with a bunch of addition, multiplication. You are going to take care of the multiplication first, and you're going to go left to right. So 4 times 4, 16. Then 5 times 7, 35. Now you are left only with addition and subtraction. Well, they're kind of at the same level of priority, so I just tackle them left to right, and here we go. 19 plus 35, 54 minus 1. And there we go. That's K12 arithmetic. Okay. So what is the deal? Sorry, in proper English. What is the deal with programming languages? So programming languages, they are going to look at this like this is not the only way to evaluate an expression. They are going to say you could define some weird operators. And in some programming language, you can define your own operators or redefine them to be more accurate. You can define your own weird operator. And you want this operator to have a higher priority than multiplication, but a lower priority than I don't know what, okay? Exponentiation, for example. So we are going to define for every operator their priority. And that tells us which one is evaluated first. So the star multiplication has priority over addition. That means we evaluate the multiplication before to evaluate the addition. To keep track of that, we are going to put all the operators of the language. So you see here some of the operators in that table that we already talked about, including comparison operators, arithmetic operators, the unary, post and pre-increment, decrement operators, etc., right? You see all the operators of the language here, including some that we didn't talk about yet. They are all ranked in that precedence, priority and precedence table. And that tells us the one at the top is highest priority, and then you go down, you lower the priority. So every programming language that you learn, one of the first things you should do when you learn a new programming language is get your mittens on actually such a table for your programming language. Keep it handy, because most likely it's going to be very similar to Java. But if for whatever reason the programming language has a little quirk, in its syntax and the priority is different, you need to know that. So you will know that after practicing with the language for a little while. But at the beginning, you're just learning on Monday morning a new language, print out the precedence and associativity table for the operators of that language. An alternate view, I never had anybody really get stuck on this, but an alternate view that the textbook mentioned to understand precedence, is to say that when you have like an operand, like 2, you look at the operators around it, and you can say that they compete to use the 2. So highest priority takes the 2. So star is going to use the 2, use the 5, get a result, and then 1 is going to be able to be added to that result, okay? So just 2 different ways to see it. The second property, associativity, this is the one that has to do with what if I have just a bunch of addition? Do I go left to right? Do I go right to left? Does it even matter? So the third column of this table tells you about, for each of the operators that are ranked in order of precedence, tells you what their associativity is going to be like. There are only 2 associativities, left to right, which is called left associative, or right to left, which is called right associative. So if I have, for example, 2 times 3 times 5, so I use multiplication here, but if you look at the row for multiplicative operators, we have multiplication, division, modulo. So if I add 2 times 3 modulo 5, it would be the same deal, okay? All the operators have the same priority, So forget about priorities. Now we are left with something that is flat. Okay, the priority levels are all at the same level. We need to evaluate the expression. So we look up what is the associativity of the multiplicative operator. It is left to right. Therefore, we go 2 times 3, and the result is multiplied by 5. Okay, so that's left associative. Right associative would be we do 3 times 5 first, and then we multiply the result by 2. And in some cases, it really doesn't matter, right? Okay, so let's talk about the assignment operator. The assignment operator is one. There was one funny thing I need to mention here. First, I need to find it. Where is it? Assignment is at the bottom. So there's a bunch of them, right? The basic assignment operator, the shorthand, like plus equal, minus equal, etc. Some that we haven't seen yet, and then the plus plus and minus minus operators are not included in that. Okay. The interesting thing with this is that first it has the lowest priority. So when you write something like, for example, n equal 8 plus 2, that's why the expression 8 plus 2 on the right-hand side is evaluated first, and then the result is assigned to n. It's not magic, it's not arbitrary. It's based, again, on n being, on equal being an operator, having a certain precedence compared to the plus operator, right? And then as far as associativity goes, it's one of the few operator, if you look at the table, that is actually right associative. Right associative means if you have an expression with a bunch of operators at the same priority level, for example, x equal n equal 2, you're going to start evaluating from right to left. So you will do n equal 2, and then you'll put that result inside the variable x, for example. Let's take a look at an example. So it's called chaining assignments, right? So for example, given 3 variables a, b, c, a equal b equal c equal 8, it's exactly like if I wrote it this way with a parenthesis at the bottom of the slide, right? Because it's right associative. So precedence-wise, we are just using assignment operator. They are all at the same level of precedence, so there's no priority here. But then kicks in the associativity that tells me you're going to first do this. And it matters. It matters because here I have a side effect. I'm assigning 8 to C, and the result of that is 8. Then I'm assigning 8 to B. The result of that is 8. I'm assigning 8 to A, and that's it. And the result of that is 8, but then it's ignored. Okay? In case of doubt, meaning, again, if you already have experience programming, you should be able to do that stuff. Okay? I'm just reminding you at best. If you are new to programming, you are losing your footing here, for whatever reason, then you have a way out. Use parentheses. I will not deduct point if people use too many parentheses in an expression, meaning like, you could have written this expression more simply. Now, I'm not going to dock you points for that, not in this class, okay? So here, the one thing I want to draw your attention to is that you can use, of course, the parentheses to change the precedence. So 1 plus 2 between parentheses times 3. Of course, the priority of the operator is still what it is, but the parentheses are going to be actually evaluated first. So starting with the innermost parentheses to the outermost. And then you can also use it to change associativity. For example, here, like putting the parentheses around 15 plus 3, that doesn't do jack. Okay? That's the property of addition. So I still get the same result with or without the parentheses, but sometimes, like when I use division, for example, here I can get things that are slightly different, right? So again, know how to read an expression. The PQs and the GQs are going to drill you down on that. Progressively, you are going to learn the precedence and the associativity, right? And you are going to be able to look at an expression and evaluate it exactly how the computer will evaluate it. Remember, that's tracing. If you don't know how to do tracing, you cannot do anything, right? So keep working on that. But when you write code, you are on a timed exam, you're stressed, there's like 20 minutes left, write safe code. Put extra parentheses if that helps you make sure that your formula is correct. And that's it. A little bit of practice exercise here. So those practice exercises, I'm going to assign them directly from the textbook. Now we're ready. I'm not hiding any syntax anymore from you guys. So every exercise in chapter 2 is pretty much available for you to practice if you want more practice, okay? I'm just recommending a few of them here. What you are going to notice is that they don't use loops, they don't use conditional statement. So again, it's going to be like a little simpler. If you have problem with loop conditional statement, you need to work on them now for, okay? Don't wait. All right. Thank you, everyone. Give me 1 second to stop the recording. That'll be yours.